So today what I want to talk about is this kind of concept that in some sense, if you know anything about generative models, you've been kind of like waiting to hear about, which is attention and kind of like related ideas, what are called transformers. And these concepts have totally like revolutionized the way people think about neural networks in general and generative models in particular, right? So certainly GPT, right? The T stands for transformer. And so all the underlying stuff of language understanding that comes from DALL-E and Midjourney and so on is all a transformer-based architecture, at least to deal with the language part. And so that's what we're going to talk about today. So basically, last time we kind of introduced the concept of word embeddings, right? And this was generally, a key idea because, we need to know how to take a word in a language, could be English, could be Spanish, could be Chinese, whatever, and translate into a numerical vector. And in theory, that vector should convey some sort of meaning, right? So that we want the, embedding for dog to not be that far away from the embedding for cat, right? And we also kind of talked about the idea of, kind of like these simple Markov models of predicting, if I saw a bunch of words, I could use a Markov model to then predict what is the next word, right? But that's not like computationally feasible for more than a few steps back, right? So if you think about what ChatGPT can do, right, it can carry on a conversation that is clearly looking back hundreds of words, right, or even thousands of words, depending on how big the kind of buffer is in some sense, right? And so how does GPT then do this kind of referring back to previous parts in the conversation? It does it using something called attention, right? And so that's what we're going to talk about today. So GPT-3, or just GPT in general, can carry on kind of like these long, referential conversations. And again, I'm kind of putting conversations in quotes here because, it's not actually like a person talking to you. But the key concept is called attention. And attention, in turn, is the key element inside what is called the transformer block. We'll talk about that a little bit too, either today or next time, right? And so this attention idea came out of a paper by Vaswani et al. In NeurIPS 2017. And the title of this paper was, somewhat cheekily called Attention is All You Need, right? So this paper here, Attention is All You Need, is the one that proposed both the attention mechanism and also the transformer, right? So this was, again, only like, 5-6 years ago, and suddenly it's taken over the whole field. It kind of shows how quickly some of this can move. And so if you're interested in the details, Attention is All You Need is the key paper to read. And then this is also summarized in chapter 9 of the Foster textbook. I'm going to do my best to summarize it for you today. And so let's kind of like, set out how this works, right? So just like, word to word, like next word text prediction, we need training data, right? And the training data is just like a big corpus of natural language sentences, right? So training data has to be some massive corpus or library of sentences or paragraphs. And so next time we'll talk a little bit more about the source of where that stuff comes from. But as one example, GPT-2 basically used, I think we talked about this once before, kind of like outgoing Reddit links. So look at kind of like, Reddit posts that had a certain karma value, which is kind of like how much people have given credibility to a certain thing. And it went out to see, okay, what was this, excuse me, what was this article about? And then it would, kind of like slurp that data up and use it as a viable thing, okay? Okay, so the training data I think is pretty clear. And we talked also last time about, some of the innovations of these word embeddings were that they didn't necessarily use individual words, but they also used something called tokens, right? And so the idea was that we have input text, right? So the input text might be, whatever. I've been playing there's a game called Jump Drive on Board Game Arena. So Jump Drive is a cool card game, ... And instead of, using each of the words as, the chunk, tokens are basically like, larger than single characters, but usually smaller than words. Right? Usually they're like kind of, chunks of, syllables is the wrong way of actually how it works, but it's close to that, right? I would imagine that they're kind of like, common 2 or 3 character chunks, right? And the reason that you chunk them up in terms of these, longer the letters, smaller the words, is to let you deal more, nicely with words that may be out of the common dictionary, right? So like proper names or names of people or cities or something like that. If you didn't have some way of dealing with that kind of stuff, otherwise you would just kind of map all that stuff to some sort of like unknown token that you'd never be able to kind of reason about because, Saskatchewan and, Mary Poppins would get mapped to the same, unknown token. That would be bad, right? So you want to have like, some sort of, more granular, but not all the way down to the letter level, okay? And so the kind of way this works is that you take your input text and you tokenize it, right? So you have your input text. That gets broken into a series of tokens. And this is not an embedding. This is just like chopping up the input into, little pieces, right? And so this tokenized result may look something like just a list of, elements in my long list of tokens that I know about. So now I've turned the sequence of words into a sequence of numbers, okay? And then this dimensionality of this could be in the, tens of thousands or something like that, right? And then what are we going to train on, right? So we have basically, this is my sequence. I could turn this into my input sample is basically a vector, right? So here's maybe one input. And then my output sample is just going to be the same vector shifted by 1 unit, right? So instead of starting at 112, it's going to start at 60. And the idea here is that what I'm trying to say is, okay, if I decide on these 3 elements, then I want to predict this next thing, right? So this is the equivalent of kind of like next token prediction, okay? So this is the desired output given the input history up to that point, is the way I think about it, okay? And again, in some sense, the way that you talk is exactly, well, not exactly, I shouldn't say it. The way that you talk is kind of like this, right? So I'm thinking about how to choose my next word based on everything that I've said so far, okay? So let's think about this a little bit more specifically, right? So let's consider this sentence, or this partial sentence. The pink elephant tried to get into the car, but it was too blank, okay? So what is a good completion for this sentence? Large. Okay, so large is a great answer, right? So how do we know that large is a good answer? Okay, so, when we say large, we want this to have a high score, right? How do we know the answer is not slow? Well, we're not talking about a sloth, we're talking about an elephant, right? So in some sense, slow kind of has to do with, the speed of the animal, right? So to figure out that slow is a bad completion, I have to look back and think about what kind of animal do I have, right? To think about, another completion might be scared, right? It was too scared. But, this is, not haunted house, it's car, right? So in some sense, I'm looking back to car and maybe also to elephant to understand that an elephant is too big to fit into a car, right? But also just in general, scared is the wrong completion because car doesn't make any sense with scared, right? Or I could think about like fast, right? Tried to get into the car, but it was too fast. Well, if this was, instead of get into, it was catch, right? The elephant tried to catch the car, but it was too fast. Then maybe that would make sense, if it referred to the car and not to the elephant, right? So in that case, the pronoun it depends on whether I'm talking about the car or whether I'm talking about the elephant, and it's kind of vague, right? So in all these cases, we are paying attention to different parts of the sentence to figure out what the right blank should be, right? And there are some words like, pink doesn't really have any bearing on what our completion should be. And some of these filler words like the and but and so on are also maybe not playing a big role, right? And of course, the critical idea is that we have no idea where these words that we should be paying attention to are in the whole sequence, right? There's no a priori way that we can guess that the key word that we care about is 5 steps back or 15 steps back, right? Which means that somehow GPT has to be looking back at quite a long chunk of stuff and figuring out, okay, so what thing should I be paying attention to that may be quite a ways back, okay? So that's the concept of attention, is just in the same way that you as a human are subconsciously kind of thinking about other stuff that happened in the sentence, we need to design a machine learning way that will also have this kind of concept of looking back and figuring out what seems to be the most important, okay? All right, so how does this get kind of like formalized in math, okay? So the key concept that makes this work is a system of what are called queries, keys, and values. And so if any of you have ever done a sort of like database programming or something like that, I think that this is kind of a familiar idea with queries and keys, right? To me, the first time I read about this, I was like super confused, right? And so one thing that I'll say is that, in addition to what I'm talking about here, there are a lot of good resources for understanding attention and transformers on the web. So here's one that's very well known called the Illustrated Transformer by this person, Jay Alamar. And so if you look, this is like a super like step-by-step, pictures and graphics and explanations, query keys and values. So like if you want to supplement what I'm talking about, this is a great place to go and take a look at. So what we're going to do, and coming back to the concept last time of embedding, right? So kind of what we're going to do is we're going to learn an embedding or a couple of embeddings for these words and tokens, and then we're going to learn a bunch of weights. In some sense, it's actually, from a linear algebra perspective, not that complicated what we're doing. It's just like a little bit confusing at the beginning, okay? So first of all, what we're going to do is we're going to set an embedding dimension. Let's call that d sub e, okay? And what that's going to do is map from tokens to vectors, okay? So we have basically, and here I'm going to be a little bit slangy to say, just let's assume that the things work like this. Right? So if I'm going to embed my string, and again, let's leave it aside. Let's suppose that every word goes to a token just for sake of argument. Each of these things gets turned into a token, and then that token gets turned into a vector, and then these vectors all have length d sub e. Okay, and so that's a choice that I get to make when I'm designing my system. And so the query, the Q part, is basically a representation of the current task, right? So if I go back to my elephant example, what I'm trying to do is I'm trying to predict what word should come after to, okay? So the query is a representation of the current task in front of us. And in this case, it's like saying what word follows 2. Okay? And we represent this like another vector. Okay? So let's kind of go back to the last element of this, right? So maybe I'm at the point where I have, my word I is 2. I tokenize that into some value. That value gets embedded into a vector of length dE. And then I'm going to further get out of this a query vector, qi, that may be a different size than the embedding. So this dimension has dimension, let's call it d sub k. Okay? And the way that this qi is formed is by taking a weight matrix and multiplying it by the embedding, right? So this embedding is basically a dE by 1 vector. This wq is a dk by dE matrix, and that means the query is a dk by 1 vector, okay? And let me just say in advance that when I've seen this represented in other things, like I think if you look at that illustrated transformer blog, you may see things kind of transposed. For me, it's always much more natural to represent vectors as column vectors instead of row vectors, but I've also seen it done where it's more like the row vector is on the left and you multiply it by a matrix on the right. It's all the same thing. So just, if you're looking at this somewhere else, you may see it flipped around, but it's all the same linear algebra, basically. Okay. And don't forget, what we're doing is, we're going to learn this embedding, and we're also going to learn this weight matrix, okay? So that's the query part. And then what I'm going to do is I'm going to make a bunch of key vectors, okay? So the key vectors are representations of each word same dimension as the query. And the interpretation of these is basically, how helpful is each word for the task? That's kind of how to interpret what these mean. So what I'm going to do is, again, I'm going to take the embedding that I get for a given word, and I'm going to have a different mapping that looks like this. Let's call it k sub I. That's another weight matrix, wk, times the embedding, right? So again, this is the same dE by 1. This is the same dk by 1. And then this here is a different weight matrix that I have to learn. And then what I'm going to do is I'm going to use the dot product to take each key vector and the query vector and dot product them together to get some sense of how much weight I should be paying to that word, okay? And that's what the attention is, right? So what we're going to do is we're going to, we dot product each key vector with the query vector to get an attention score or an attention weight. for each word. So that's like saying for the ith word, so j basically is going to go from 0 up to, the ith word. This is more or less the dot product of the query vector with the key vector, right? With the key vectors. I can only do this for things that have the same dimension, obviously, right? Now it turns out it's not exactly this. First of all, there's basically the idea is this is a normalization. So there's going to be a normalization where I'm going to divide by more or less the square root of the length of the vector, and then I'm going to do a softmax of the result. So kind of the idea is that when I do this, I'm basically taking all the dot products, I'm normalizing them, and I'm making sure everything adds to 1, right? This is what softmax does. So, all the attention weights will then sum to 1. So if I kind of look back at my pink elephant example, that's like saying, I have the pink elephant. Each of these, words will get turned into a key vector for the given task I have. And then what I'm going to do is I'm going to take the, so say that, 2, I'm running out of space here. So let's say that 2 is basically word 8. So my query vector is like, q sub 8. And then I'm going to form a bunch of dot products with each of these possibilities. And then I have to normalize these dot products so everything adds up to 1, right? So at the end of the day, the weights I have may be like, 0.01, 0.02, 0.2, ... So the higher the weight is, the more relevance there is for that word to play a role in the prediction, right? So again, going back to our example with the pink elephant, we said that 2 blank, right, will definitely depend on elephant, but it won't depend very much on pink or the or anything like that. And that's the hope of what happens when I do this vector product, right? And again, one thing to realize is that this weighting will definitely change based on, as I move my cursor down the row of words, what words are important for the task may not be the same for every prediction, right? That's going to change around every time I predict a new word, okay? And finally, there's something called the value vector, right? So kind of what we're saying is that each of these weights is telling me how much attention I should pay to that word, but then I have to kind of represent, okay, so what does that mean to pay attention to elephant, right? Elephant right now is still just a token. It's still just a number, right? So now I need to have another basically weight matrix that will turn each of these words into features, okay? So the value vectors are basically like unweighted word features in some other dimension. Right? This is like saying, independent of the attention that I'm paying, what I do is I form a vector that is yet another weight matrix times the embedding, right? So here, this thing is still the embedding dimension. This here is some, more weights that I have to learn. But now, I don't really care about making the dimensions of this consistent with anything. This can just be some new dimensionality dv by 1, okay? And so, dv could be different than whatever the dimensionality of what I used in the query in the key, okay? And finally, the idea is to combine these all together using the attention weights. It's like saying, okay, independent of knowing what attention I want to pay, each of these words is getting transformed into a feature vector in some other space, right, which I'm going to learn. And then the final step is to say, okay, I have, the pink elephant. I turn these into, value vectors. These are my like VI. So this is like, V0, V1, V2, ... And then I'm going to multiply these by, for my current task, the attentions that I got in the previous step. This is like saying, okay, if I'm trying to predict, word number 8, I'm going to multiply my attention by this vector. So it's kind of like a weighted sum of these vectors. And the result will be a single vector that is the same dimensionality as all these guys. And we could call this Z8, let's say. This is called the final context vector. So the context vector is the output of the whole thing, right? It's like saying, I'm going to take all my input words, I'm going to assign them to some features, some sort of space. I'm going to look at my current task, which is my next word prediction. I'm going to weight each of the words by that amount, and I got that weighting based on a little different process of query and key. And then my final kind of input to my neural network is going to be this new thing that kind of, in some sense, is combining all the stuff that I learned about the previous words, okay? And so this whole thing, this whole set of stuff is called an attention head, okay? And so you may have seen in a paper, if you've been reading about there's multi-headed attention and so on, right? So kind of the idea is that, you can do several different versions of this, right? In the sense that once I go through this process once, I'm in some sense fixing the attention that I'm paying to the previous words, right? But it could be that I want to have, just in the same way we kind of talked about, multi-hypothesis, keeping multiple ideas in mind, we could have several of these heads that are each allowing the algorithm to focus on different words, right? And we're going to combine these opinions all together at the end. So it's like saying that, this whole process, so this whole process that takes, all the input words, goes through this whole query key value thing and comes out with a Z, right? Which is kind of what we're calling the context vector. There's no reason that I have to restrict myself to just one such vector. So this whole process like this is called an attention head. Okay, and we can have multiple such heads. Which allow basically kind of like attention to be paid at different points of the sequence. So in our example, maybe one attention head turns out to really be focusing on the elephant, and one attention head really turns out to be focusing on the car, and one attention head is focusing on the verb, right? Now, of course, ultimately we have to combine all that stuff together into one single thing, which I'll talk about in just a moment, but that's kind of like the basic idea. So I know it's confusing the first time you see it, at least it was for me. So any comments or questions about just the mechanics of it? The kind of interesting thing is that there's no really complicated math here, despite how, to me, complicated the whole thing seems. We can kind of break this down into very simple linear algebra, right? So we can write all this very efficiently in matrix form. Which is to say that, if I think about, if I have n is the number of tokens in my sequence, I can think about kind of doing this all at once, right? So I could say, okay, I have a set of tokens, right? These are basically my x's. This is like I have n embedded vectors for the input. I have a big weight matrix for the query, which will assign a key vector to each of these things. So the output is going to be a dk by n matrix that contains all the query elements. And then I have, similarly, a key matrix that is going to be dk by n, and a v matrix that is going to be dv by n. And then the overall z that I have going down the line, and I need a transpose here, is going to be the softmax of weighting by this value, q transpose k. That's the attention values. This is going to be basically a vector of attention value, or a matrix of attention values. And I dot that with the values. So this is going to be like a big n by n matrix. I multiply this by my values, and then I get a set of context vectors. So like I said, other papers use row vectors for this instead of column vectors, so you may see this in a slightly different way. So this is the basic idea. The only thing that I need to do to make this work in matrix form is to make sure that in this n by n matrix that I'm not looking into the future, right? Because I can't, in GPT world, be thinking about like looking into future words to predict by current word. What I need to do is kind of like make a little mask that looks something like this. So I kind of have like a stair-steppy thing that says, all the values in here are minus infinity. And this is kind of like a causal mask that makes sure that none of the words in the future have any contribution at all to the softmax at the end. Those all just get zero attention. So there's a little bit of a clever trick in the middle where I multiply by this thing that says, hey, no looking into the future, right? Especially important when I'm doing training. And then I mentioned that basically there's this idea of using multiple attention heads, right? So the way that this works in matrix form is like saying, okay, I have my input. I put this into an attention head here, some other attention head, and so on. So say I have like 4 attention heads. Each of these results in a different context vector. What I can do then is, let's say that there are, if there are h heads, what I can then do is I can kind of like concatenate these into a single vector, right? So I can concatenate into a long skinny vector like this. And then I can multiply this times this long skinny vector to get something that is basically the same size as one of these, right? So there's yet another weight matrix. That's basically saying, how do I then kind of weight all of the outputs and opinions from the many different attention heads I may have? At the end, I only get one kind of heat map of attention on all the previous tokens, but I'm letting there be this intermediate step where I'm kind of considering multiple possibilities, and then I learn another weighting matrix that's going to kind of like trade off all of those things. So basically, the learning process is learning these various weight matrices, right? I have the query, key, and value weight matrices. I have this thing that I deal with if I have multiple attention heads. And that's kind of what's happening, okay? All right, so let me pause and ask again, questions or comments about the idea? Again, a little confusing, but if I refer back to this, and this is, again, part of my philosophy, is that certainly there are a lot of great slides, for example, these, that illustrate things with like, nice colors and so on. And I think that this is actually a nice way of thinking about it, right? And so I encourage you to go back and think about this. But also at the same time, when I'm lecturing, I don't really like to just like flash through a bunch of PowerPoint slides, because otherwise I feel like I would have been through this lecture in 10 minutes, right? So by my writing things down slowly and intentionally, I feel like I'm giving myself a little bit of time for it to sink in for you guys, as opposed to just doing PowerPoint. So that's just my strategy. But there are many nice, more graphical slides that make all this happen. But it's all the same stuff. There's like the multiple attention heads. And so I think that if you want to read more about it, take a look at something like this. But let me just say that this is like an illustration of the way attention is being paid. And actually, just to switch over to the actual thing happening, so there is a nice GPT example in the book. We didn't talk about the transformer yet, but we're going to get to that in a moment. But just to kind of skip to the end, this is a data set that is based on wine reviews. And so what they did was they took, I think it was the Wine Spectator, they took all these like little tidbits of, like 40, 50 word each descriptions of wines, right? And this data set had 130,000 such descriptions, and it just kind of cropped out everything but the, took all the metadata out and just found this as the description, okay? And then you can kind of see what we were just talking about. So we're taking this, we're tokenizing, right? This is kind of like words kind of coming into tokens for a given example. And if you want to drill into this, you can see like what the tokens actually correspond to. This is like the input, right? And this is the output. You can see that the input is simply, or the output is simply the input shifted by 1, right? So the output is 10 to 42, which is like the same as the input, just starting from 1 unit later. And then this is the causal mask function we were talking about that shows that you want to make sure you don't pay attention to words in the future. Transformer we're going to talk about in just a second. And then at the end, what I want to show you is the attention part, right? So here, this is kind of like showing a heat map of how much attention is being paid in the end to certain words, right? So this is, again, a wine review where it's fed in with this kind of starter input, wine review Germany. So it's like asking, okay, generate a German wine description, right? And so it starts to focus on different words, and you can see that the kind of heat map of the, let's scroll down a bit. The heat map of the words is kind of like equivalent to attention. So the darker the word is, the more attention is being paid. And as the, as the sequence goes on, you can see that, for example, to predict, elegant, right? It's looking back at surprisingly, right? But it's also always kind of paying a little bit of attention to review and Germany, right? Even as the sequence gets to be fairly long, there's still non-trivial attention being paid to some of these early words. And this is, again, the magic or the virtue of attention is that even as we go all the way to the end, Germany is still being highlighted a fairly often amount of time, which means that, I'm no wine expert, but basically it's probably looking to Germany to get some sense of what are the characteristics of German wines, right? It has to remember that, keep that in mind, right? And there's no way to like hard code that in advance. And so kind of what I'm going to ask you to do on homework 3 is to do something very similar. I'm hoping that you can use the same structure of this GPT to be able to take your own text that you've gotten from somewhere and just plug it in and see how well it works. Now, I'm not sure how well it will work if you don't have 130,000 examples. I'm hoping that it will do something, right? It's possible that maybe you could take GPT here and kind of train it off the top with some additional text that you provide. I'm not sure how well that works. So again, this is going to be a learning experience to see how well you can do it on your own, but I'm curious to see. Okay, so questions or comments on anything I've said so far? All right, so let's talk about what is a transformer, right? So transformers, fundamentally, there's not that much more to say about transformers besides the key concept of attention. Once you know what that is, then life is pretty good. And again, let me just say that transformers have overtaken computer vision in a lot of ways. And so if you look at the lecture notes, for example, there's a whole course at Stanford that they taught called Transformers United, right? And so you could take a whole class on transformers, right? But this is more like applications of transformers and refinements of transformers rather than the fundamental transformer idea, which is, I think, something I can explain in the next 10 minutes or so. But if you want to learn more about this, there's like a zillion other things that you could learn about, right? So there's no shortage of online materials about learning about transformers. I linked to the Stanford thing. There's also this nice thing called Transformers from Scratch that has a nice kind of linear algebra way of looking at this. So again, when I was writing this lecture, I referred to a lot of these kinds of things to figure out how to explain this in a way that made sense to me. And finally, I linked to this website. So Stephen Wolfram, I'm sure that you probably have used Wolfram Alpha at some point in your lives to calculate something for probability or signals, something like that. So he was the founder of Mathematica and many other things. And so he wrote this post earlier this year on what is ChatGPT doing. And again, just if you take away nothing else from this chunk, I want you to realize it's just adding one word at a time, right? That's all it does. And so this is, again, I think a very readable, somewhat more public interest or public-facing way of thinking about how it works. But there are many ways to explain this stuff. So please take a look if you're interested in more of that kind of thing. But let me talk now about just transformers, okay? So this query key and value vectors, the embeddings, everything is trainable, okay? And so all this results in this context vector, which is like a blended opinion of all the attention heads about what features should be put into the network to be the next task, okay? And so a transformer block is basically like a multi-head attention layer with a bunch of skip connections and other layers in between. But fundamentally, it's a multi-head attention layer, okay? And so a transformer block is basically a multi-head attention layer with various normalizations and skip connections. And so let me just do a very high-level sketch. So basically, the input to the transformer block comes in. It gets split off into these query key and value vectors. Okay. These get fed into like a multi-head attention block. Hyphenate attention, okay. And then there is a skip connection that basically goes around from the query to here, as I understand it. There's some layer normalization. Then there's a bunch of dense layers here to process the output. There's another skip connection that goes around this guy. There's another normalization of the output. And then this is the output. So the key thing is basically the multi-head attention block that comes from what we just talked about earlier, okay? And then I'm not particularly interested in talking about the details of these normalization blocks because, again, I think this is something that is not super important to understand the basic idea, okay? And remember, these skip connections are basically like highways that allow you to bypass certain chunks of the network so you can transfer information forward directly without having to kind of learn or work backwards through the network. Okay. So it's the basic idea. Okay. There's one more thing that makes the transformer thing work, and that is observing that so far there's nothing that we have enforced that really, other than the causal mask, is looking at the order of the words that are coming in. Okay? So for example, let's suppose that we had these two sentences. The dog looked at the boy and blank, versus the boy looked at the dog and blank. So for example, we know that barked is a good completion for the first sentence, and I don't know, smiled or laughed is a good completion for the second sentence. But if I'm thinking about just the raw attention that I could pay to the previous, 7 words or whatever, there's nothing that really forces me to understand the sequential order of boy and dog, right? I can imagine that the same attention could be paid in both places. How would I know the difference, okay? So the extra step, the secret sauce, is this idea of positional encoding, okay? So we talked about positional encoding back in the diffusion lecture, right? Remember we had this, so how to disambiguate, or how to disambiguate. The key is what's called positional encoding. Right? So when we talked about diffusion models, let's refer back to the diffusion model lecture. There was a point where I had this alpha value, which is kind of like how much noise am I adding to the image at any given time, right? So this was basically a scalar value. And what I wanted to do was to input, remember what we were doing with reverse denoising, right? Or reverse diffusion. We were saying take a noisy image and make it a little bit less noisy, and the input is the noisy image and the alpha value that says how much, noise do I want to undo, right? I need to find a way to make that alpha value kind of compete with the huge dimensionality of the image and have that play a big role in the learning of the network, right? So what I need to do is turn this into a matrix. And remember that this matrix was basically like cosines and sines of different frequencies. And I don't think that I have a picture of it at my fingertips from the diffusion lecture, but let me see if I can find it from one of these other blogs here. Not here. I know you guys can't see what I'm scrolling, but that's okay. Actually kind of surprised that I can't just dig out a positional embedding picture here. Oh yeah, here we go. So here, this is again from the Illustrated Transformer blog. So the idea is that I can take a number and I can turn it into a matrix, right? So I'm taking a set of 20 words, and so 20, like 0 through 20, is the index of the word in the preceding phrase, and then the corresponding vector in the kind of like row dimension is turning that number into a vector, right? And the idea is that the vector is unique for each of the input numbers. And so that's exactly what I want to do here, is I want to encode, I guess if we're cutting from 0 like good, programmers, right? So what I want to do is I want to associate each of these words with its index in the sentence, right? And I want that index to play almost as important of a role in the network as this whole like attention head part, right? And so the way it generally works is what I do is I take, suppose that I have my sequence length So say I have like n tokens. This is my embedding length. And so if I didn't know anything about positional embedding, I would just begin my input to the transformer block by embedding the words into tokens, right? But now what I do is I add a positional embedding matrix that is literally just the same size as this matrix, right? So these two matrices are the same size. And then this sum is what I put into the transformer block. So already the thing that I actually do in the transformer is a little bit different than what I showed you in the very beginning, which was more or less this back in the initial part. I'm not just embedding the words, but I'm also adding to that a positional embedding per word, so that it definitely alters what actually gets put into the whole thing. And as far as I can tell, it's always just a straight addition. Like there's no weighting between the positional embedding and the token embedding. It's just like a straight add-on, right? OK, so the last thing I'll say about this kind of like transformer thing is that just like with everything else, we use more than just one of these transformer blocks, right? So for example, I believe that GPT-2, the original GPT paper, was something like this. And of course, things are much different now with GPT-3 and GPT-4. In fact, some of the architecture of these later GPTs, we don't even know what it is. But the idea would be, OK, high level, I take my sentence, the pink elephant, whatever, ... This goes into a text plus positional embedding block. Then this goes into not one, but many transformer blocks. And so the original GPT paper was actually 12 transformer blocks in a row, right? So the very first transformer block has the input of the words, right? But then afterwards, I'm basically taking the output of the transformer block and I'm feeding it back into the next transformer block. And so what's coming in there is just like some vectors, right? And I do that 12 times, right? So why 12? Why not? Just like any other neural network question, right? I think the answer to why 12 was that it was what they could fit into their GPU memory at the time, right? So, and then at the very end of this, I have basically a dense block, and then I have a big vector. And this big vector is the same dimension as the vocabulary of words that I have. And then at the end of the day, I have a softmax, basically, that I guess this is the result of a softmax. So all these numbers here add up to 1, right? And so then what I could do is, just, for example, if I want the output to be big, right? If we said that large was a good completion of that original example, right? So hopefully, at the end of this whole 12 transformer block thing, large is going to show up as a big value in my softmax vector, right? That's the hope. And of course, given that the way we know ChatGPT works, apparently it works pretty well, right? So the last thing I want to say about this is that obviously you get different results from GPT, even though you may put the very same input in, right? So it's not entirely deterministic, right? So what accounts for the noise? In some sense, what accounts for the noise is that something called temperature. So you may see in these algorithms something called a temperature parameter. So the temperature is kind of like a setting for how variable the outputs of your next word prediction thing are going to be, right? So if I set the temperature as 0, I basically get deterministic output. which basically means, the word with the highest probability after the softmax. Right? Because I can think about this vector of, stuff over the whole vocabulary as a PDF, right? And so I could just say, okay, I'm just going to pick the most probable word, right? If my temperature is equal to 1, this would be like saying I choose the next word according to the output PDF. Kind of what that means is, maybe since I have like tens of thousands of words, the biggest contributor to the softmax may not have a huge value. It's probably not going to be like 0.95. It may be like 0.4 or something like that, because there are many words that could fit well, right? Large, big, gigantic, whatever. Synonyms and a bunch of other words too, right? And so the idea is that I can treat this as a PDF and just say, okay, I'm going to choose a word based on sampling from this discrete PDF, right? So most of the time that word shall hopefully make sense, but it could be that scared is a possible word with a very low value, and I just happened to hit a random number generator that made me choose that by mistake, right? And so typically, what you do is, you set your temperature, and it's said that higher temperatures are more, kind of what we would call adventurous in terms of how it strays from the most likely word. So you get, less accurate outputs in some sense, but also it gives you more diversity in what you're able to produce, okay? And so just kind of an example that I noticed that in the wine example here, that here's an example of temperature, right? So if I scroll up a little bit, I can see that the temperature parameter here is set to be 0.5, right? And also, I guess you can see, look back, this is like saying, look back at most 80 tokens, and then this is a temperature that's close to the middle range, right? And here I can see that these are like the top contributing, answers, right? So in some sense, these numbers here should add up to 1. Scrolls up a little bit. So these numbers here should add up to 1, and you can see actually that the most likely output was a wine called Moselle, right? But the temperature parameter was high enough that in fact the number that got picked, or the word that got picked was, sorry. Of course it picked this moment to disconnect from my thing. The thing it actually picked was Franken, which had only a 4% chance of being predicted, right? So here's an example of the temperature thing in action, right? If the temperature was set down to 0, I for sure would have picked this Moselle, but the fact that I'm allowing some sort of diversity let me pick this thing. And if again, let's look at some of the generated text, right? So if I kind of scroll down here a little bit, well, I guess we can scroll up a little bit to see, here's some generated text, right? And let me just make this a little bit smaller on the OBS screen. I'm not sure why this is like cut off a little bit. So, wine review, Germany, Franken silver. While intensely fruity, this dry Sylvaner is surprisingly elegant. It's not a big wine, but it's a bit soft and sweet with a nice savory honey note to the finish, right? Definitely makes sense. It's grammatical, right? Certainly, I think you could probably find some examples of generated text that don't make, like here's an example, right? The mouth is firm and very dry while the flavors are out of the grapefruit, right? So there's something that doesn't quite make sense there, right? But still, for a thing that I trained on a machine downstairs with one good graphics card that didn't take like days and days to train, it's pretty impressive that this works, right? So again, I'm hopeful that using your own data sets, you'll be able to get something that at least makes some sort of sense. Okay. And so since this is a class about generative modeling, I guess I should say that this framework is what's called a decoder transformer. There are things that are called encoder transformers. So let me just say real quick that all this describes what's called a decoder transformer. There are also, as you may guess, what's called encoder transformers, which I'm not going to talk about here. So encoder models, basically, the difference is that they're not causal, right? So you may have heard of an embedding system called BERT, which is a Google thing that basically takes a sentence and produces an embedding. So if you're doing some sort of like offline sentence translation or sentiment analysis, something like that, where you've got the whole corpus in front of you and there's no sense of producing something on the fly, then you don't have to have this sort of causal masking in the middle of the attention layer, and that's called an encoder transformer. So basically, let's just say, e.g., BERT, which I believe stands for bidirectional encoding something transformer, which more or less means that there's no causal masking required. And also, I'm not going to talk about it right now, or maybe even at all, but there's also something called vision transformers. Which you see sometimes called this, right? The reason I'm not going to talk about too much is I don't feel like for the stuff that I want to talk about in terms of generative modeling, I didn't see a lot of stuff I needed you to know exactly what that meant. But you can imagine that you could apply the same kind of idea to images instead of words, right? So you can imagine that if I'm trying to, classify something or detect something, what I want to do is think about kind of like a, heat map that kind of like outlines regions of the image that I want to pay attention to make my decision, right? And so this attention kind of can come from this whole idea, except instead of using words, I'm using pixels, right? And I can use the very same idea of a positional encoding of pixel values to figure out where I should be paying attention to do some sort of downstream task, right? And so basically, this is just like using pixels instead of words. But I kind of wanted to hold off on talking about attention until we had gotten through all of the other stuff. And I thought it was more natural to talk about it in terms of words than in pixels, right? So this is kind of like, again, key idea. I guess I should say that I told you previously that I thought I'd gotten through all of the key underlying algorithms with diffusion models, but actually I forgot to mention that transformers is the other key thing. So now I think with the addition of transformers, I think that pretty much you could look at any kind of like, generative modeling paper, at least understand what most of the words mean, right? Because I think that these are all the kind of key pieces that we need. Okay, so let me pause and ask questions or comments about anything. Okay, so the next lecture, I'm not exactly sure how it's going to go. So kind of what I want to talk about next time is large language models, but a little bit more from the social and ethical side, right? So I'll talk a little about the technology, but I do want to kind of preview and say, I want to talk a little bit more about the kind of social implications of how these models are being deployed and used, right? What they cost us as a society, right? So if I go back to, you should probably look ahead to the next lecture. So the readings and the links for the next lecture are more about, can we believe what GPT-like algorithms produce, right? In particular, I want to talk about this paper called On the Dangers of Stochastic Parrots, Can Language Models Be Too Big? This was a very important paper that came out a couple years ago that kind of is pushing back against the purely computational view of language, right? Whereas some people might say, well, GPT makes perfectly great language, so it's thinking like a human, right? And this is a counter argument against that. You are not a parrot, right? Is another way of thinking about it. And so let's talk about that. And I also, in some sense, I'm not exactly sure how that lecture is going to go or how long that lecture is going to be. So I want you to kind of come prepared to talk to me a little bit about let's have a conversation about this, and we'll see what we can dig up in possibly real time about some of these implications. So that's going to be next time. We'll see how it goes. If we ending up early next time, that's not the end of the world. But come prepared, and I'd like you to read ahead a little bit on some of these things so we can talk about it. All right.